Hi, in this first section we're going to talk about the beginnings of programming, the first programmable machines and the first high-level programming languages, because this is where all the modern languages date back to. This is where all their ancestor languages are. And many traits that we can see in modern programming languages are actually decades old. So first we'll talk about programmable machines, not necessarily digital ones, but much older machines that were just mechanical. The first models of computation, which were highly influential and still used today. Then we'll consider first digital computers and the programming languages that were used to code for these computers, the first high-level programming languages. And we'll start with programmable machines section. So probably the first programmable machine was not actually made for computation, but was rather made for fabrication. And this was the Jacquard loom machine that used punch cards, so a system of programming, basically the process of weaving. And using punch cards and a clever mechanism that processed these punch cards one by one, this machine was able to weave an intricate picture on a fabric piece. So this was not, of course, a computer. So this was rather an industrial machine, maybe one of the first industrial robots, one might say. But this was influential because the next thing to consider here is the first real programmable machine. So this is, by the way, a punch card of a much later machine, one of IBM computers. This is like what evolution punch cards have undergone from Jacquard Loom's punch cards to IBM computer punch cards. So the first real programmable machine was Babbage's analytical engine. It was actually a theoretical concept, and Babbage started to build this machine around 1830s, 1840s, but this computer was never actually completed. It was never built in its entirety because it turned out to be too much of an effort. And this couldn't be justified by the requirements of those days. So the engineering was not on the sufficient level, and the finances required were too high. Still, this is considered to be the first programmable computer, a mechanical programmable computer, and Babbage was influenced much by this punch card technology that came from Jacquard's loom. Also, here is where we can say that we have a first computer programmer, because Ada Augusta Lovelace was the first person who created a program for a programmable machine. So she described a way to compute Bernoulli numbers using Babbage's analytical engine. Um, so, of course, the middle of the 19th century was not the time when the world saw first digital computers. But actually, if we speak even about mathematical models of computation, of digital computation that we use nowadays, these models also predated the actual digital computers. And probably the most important model of computation, the mathematical way of describing what a computation is, what an algorithm is a Turing machine model. So this was proposed in 1936 by Alan Turing before the first computer was made, the first digital computer was made. And this is a very simple device. So it is a concept. Here on the right hand side of the slide, you can see like an actual Turing machine that was built as a hobby by some engineer. But obviously, when Alan Turing proposed this concept, it wasn't meant to be actually implemented in hardware. So the concept is pretty simple. What is really an algorithm? Turing thought probably. So an algorithm is some sequence of steps which is fully graspable. So this sequence of steps should be storable somewhere, and it should be finite. But using this sequence of steps, we should be able to process potentially unbounded amounts of data. Well, finite, but unbounded. So this means that there shouldn't be any limit on the amount of data that a single algorithm can process. Well, as an example, we have many ways to sort an array of numbers, a list of numbers: bubble sort, merge sort, quick sort, etc. And so all these are finite algorithms. But the size of the array, which we can process using these algorithms, at least in theory, is not bounded by anything. And to capture this thing, that algorithms themselves are finite, bounded, kind of known, deterministic sets of commands, while the amount of data shouldn't be really bounded conceptually, is covered very well by this Turing machine concept. So Turing machine is a virtual device which has a tape, and in every cell of this tape, a sum symbol can be written down. So in simplest case, we can have just zeros, ones, or say an empty piece of tape. In principle, we can enlarge this alphabet of symbols that can be written on the tape. So the tape is divided into cells, and thus it is a digital device, we can say, because there are clear boundaries between these kind of cells of memory on this tape, and there is a finite predetermined set of symbols that can reside in every cell. And each cell can store just one of these symbols. Also, we have a head which runs above the tape, or we can say that the tape runs below the head, like in a tape recorder. And this head observes only one cell at a time. So at every moment of time, this head is above some particular cell of the tape. It observes the symbol in this position, and based on the symbol that it observes, and based on the current state of the head, the Turing machine performs one of several possible actions. So it can write some new symbol, erase the old symbol in the particular cell of the tape, write a new one, and also it can move but just one step to the left or to the right. Or it can halt, so it can stop the computation, and we can say that, okay, so the program has completed. And we can read out the contents of the tape, and that will be the result of the computation. So you can see that everything is pretty bounded here. Everything is kind of very localized. So it is not a random access memory where like we can say, okay, let's go like 1 million cells to the right or 1 million cells to the left at a time. No, it's very local. So at every moment of time, we can move just one step forward, one step to the right or one step to the left, and we can modify only one cell of the tape, the current cell of the tape, at every single moment of time. And the head of the Turing machine can, of course, come into some new state. And the number of the states possible for this head of the Turing machine is finite. This is very important because this captures the kind of essence of an algorithm. An algorithm should have finite set of commands and finite set of kind of states. But the data, the contents of the tape, the memory can be potentially unbounded. So it shouldn't be bounded by any specific number. And here you can see like one of the possible ways to depict a Turing machine program. So this is essentially a diagram which lists the states of the head. So here we have the starting state, which is by definition the state that the head is in when we kind of turn the Turing machine on. We have some intermediate states A, B, and C. and we have the halting states, the halting state. So when we come to this state, the Turing machine stops and we can read out the result. And also we have these arrows from state to state. For instance, we can see here an arrow from B to C with a label 0/0L. This means that if the current state of the head is B, and if we observe symbol 0 on the tape, then we write 0 on the tape. So basically we don't change this 0 symbol. We move the head to the left, one step to the left, and the head state transitions from B to C. So this whole transition, like one step transition, is here denoted with a labeled arrow, labeled link from B to C. So this is a diagram which is pretty easy to read, and using just this diagram we can deterministically say like what will be the contents of the tape after we place the head at a particular cell of the tape, having something written on the tape, and after we run this Turing machine. So this device clearly can be simulated on a modern computer, and I will provide you with a link to some simulations, and we'll see that actually some simple programs are not that hard to design for Turing machine, like checking contents of the tape for being a palindrome, so a word which is equal to its mirrored image. We can write a program which adds one, like increments a given number written in its binary form, etc., etc. But of course, you can imagine that writing any like real-world algorithm, like sorting an array of numbers, each of which is written in binary form on a tape, is a very, very tedious task on a Turing machine. But it was not designed for actual programming. It was designed just to capture the essence of an algorithm. It is not even designed to kind of fully capture the notion of efficiency, so that like something can be done fast, something cannot be done in an efficient way. So these are all models that came later, but Turing machine captures a very important property of computability. Well, Alan Turing also is widely known for proposing a test which can distinguish between a human being and an artificial intelligent agent. So this test, the Turing test, nowadays plays quite an important role, at least conceptually, because nowadays we have some AI models that really challenge this test. So in this test, to distinguish between a human being and an AI agent, you start just talking with these agents, a real person and an agent, and if during a dialogue you cannot say like if you are talking to a person or if you are talking to an artificial intelligent being, then actually AI passes this test and it can be considered having an actual intelligence. Well, nowadays there are some modifications of the Turing test, but still considering the year when it was proposed, it was a very influential theoretical test for AI. So we have a very important notion, which is Church-Turing thesis. So Turing's machine was not the only model of computation out there. And practically the same year that Turing proposed the Turing machine, Alonzo Church, American logician, mathematician, also devised a way to describe an algorithmic procedure. That was lambda calculus. Here we do not dive into details about like what lambda calculus is, but we'll consider some examples later on during the course. And you should know that, Church's lambda calculus is actually quite an influential thing in mathematics, and in particular for Lisp language. one of the oldest languages, the high-level languages. This was one of the major influences. Okay, so anyways, at that time, some models were proposed. Among them, two probably most influential were Church's and Turing's. And both of them, both Church and Turing, were able to prove that if some procedure can be coded in Turing machine, if it can be implemented using Turing machine, then it can be implemented using lambda calculus and vice versa. And they were quite affirmed that practically any algorithm that existed by the time could be implemented on a Turing machine or using lambda calculus. And this made them formulate a thesis. It's not kind of an axiom. Well, probably if it is anything in mathematics, then it's closer to an axiom. But it's definitely not a theorem. It's not something that can be proved. It's just a definition of what we consider nowadays to be an algorithmically solvable problem. So the formulation of the thesis is as follows. A function on natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. So if and only if there exists a program for a Turing machine, like this kind of diagram that you've seen recently, that allows Turing machine to perform the computation, to perform the data processing, to solve the problem. Like, why here we're talking about a function on natural numbers, not just an arbitrary algorithmic problem? Well, that's because in mathematics, practically any data processing task can be described in principle using just natural numbers, because a natural number can be written down using binary notation, and so any binary data in computer memory can be treated maybe as a very large, as a huge natural number still. So when we talk about like data types, in mathematics, in principle, natural numbers are quite enough to describe any kinds of data. Using some clever techniques, like anything can be coded just with a single natural number. Well, it will be a huge natural number, of course, but still. And so any kind of deterministic transformation of data, say sorting an array. So this is a transformation which has its input as a list of numbers, which can be coded still as some state of binary memory, and then it can be coded as a single huge number. And the result of the sorting procedure is also an array of numbers. And so this is basically a transformation, a mapping from numbers to numbers, which can be described as transformation of a single number into a single number, the state of computer memory into some new state of computer memory. And so this can be, in principle, encoded as a program of a Turing machine. As all the algorithms that we have today, so all problems that are solvable algorithmically, they are solvable in a Turing machine, and that's the thesis. So that's a kind of an axiom. That's almost a definition of an algorithmically solvable problem. So here, effective method means that a problem can be solved using an effective method if this is a method so that each step is deterministically chosen, and this algorithm should end in a finite number of steps. So basically, of course, if an algorithm runs in an infinite loop, this is not considered to be a genuine procedure. This procedure should terminate in finite amount of time. And this is kind of a very important concept to learn, the Church-Turing thesis. Basically, this leads us to a notion of Turing completeness. We say that a programming language is Turing complete if it is as computationally powerful as a Turing machine, which means that we can simulate Turing machine using this language, and thus anything that can be programmed on a Turing machine can be programmed in this language. And if we believe the Church-Turing's thesis, that any algorithm can be implemented in principle in a Turing machine, if we say that some particular programming language, say Python or C# or whatever, if it is Turing complete, it means that any existing algorithmically solvable problem can be solved in principle using this language as well. So most of the modern programming languages are Turing complete, and most hardware that we use today is Turing complete, but not all of it. So, for instance, before 1940s, the middle of 1940s, at the beginning of 1940s and at the end of 1930s, there existed some computational devices, like we can say first, not really computers, but almost computers, that were not Turing complete. Well, consider basically your calculator, okay? So you are able to perform arithmetic operations using a calculator, but it's not Turing complete unless you can write programs having for loops, if then else there. Okay, so the fact that some device is able to perform computations does not necessarily mean that this device is able to run any kind of algorithm, that any problem can be encoded in this device. And the very first computers were not necessarily Turing complete devices. But by the way, the Babbage machine, which hasn't been ever built in its entirety, it was conceptualized as a Turing complete device. Okay, so just as you encounter this terminology of Turing completeness of a programming language, just make sure that this is a synonym basically for that any algorithmically solvable problem can be solved in principle using that language. But this doesn't mean that it can be done efficiently, that the program will run fast, that the program will use a decent amount of memory, etc. It just means some kind of principal ability to code any program into simulate any program in a particular programming language or on a particular piece of hardware. So then we come to first real computers. And they appeared after some years after these first models of computation were proposed. So the first real digital Turing complete device was built some years after Turing proposed his notion of Turing machine. So one of the first, if not the first, digital computers, which was Turing complete, was Konrad Zus's Z3. This was built in Germany in 1941, and well, naturally during because of Second World War, this particular device didn't get that much traction, although many ideas that Konrad Zuse used, they actually were ahead of its time. So this computer has quite low clock cycle, so it can perform just several operations per second, and it was pretty large a device. The first computer which was purely digital and had much higher efficiency was ENIAC computer, which was built effectively. The building of this computer was finished after World War II. So you can see the difference in computing power here, in processing power. So this computer had a clock cycle of around 100 kilohertz, and it was able of carrying out about 500 floating point operations per second. So this means that FLOPS, floating point operations, means that you can add, subtract, multiply, divide two floating point numbers about 500 times per second, which was pretty fast and clearly much faster than any human being or even reasonably sized groups of human beings could do. So The main user of this computer originally was the United States Department of Defense, and this computer was originally used to compute ballistic tables. So at that time, in the middle of 1940s, two different computer architectures were proposed, and they are still in use today, largely. The better known architecture that underpins practically all modern consumer machines, so personal computers, is called the von Neumann architecture, proposed by von Neumann, physicist and mathematician. So in this architecture, we have clearly divided responsibilities between different parts of these computers. So we have a memory storage system, main memory system. We have a central processing unit, and we have an input-output system, right? So the notion of central processing unit, CPU, dates back to these architectures, like von Neumann architecture. This architecture supposes that both the data to be processed and the algorithm, the code, reside in the same memory. Unlike Turing machine, which by default has the algorithm encoded using states of the head, the diagram of states of transitions within the Turing machine's head, and the data naturally occupies intermediate data and input data and output occupy the tape of the Turing machine. Now here, everything shares the same memory, and so this means that the code and the data that this code processes can be uniformly input into the computer memory using the same technology, say punch cards. We have here in this architecture the notion of operational register and of arithmetic and logical unit. That's the unit that performs the operations over numbers, over like the main type of data that we have, and a separate control unit which reads out commands from memory, treats pieces of memory as commands actually, and performs the computation using that arithmetic and logic unit. So here we have already just several sub-devices within the CPU, which clearly have their own clear responsibilities there. So unlike von Neumann architecture, we have hardware architectures, well, which makes distinction between the storage for the code and storage for the data. So in hardware architecture, code and data occupy completely different independent spaces within computer memory, and there can be just different technologies of memory even to store code and to store data, and input technologies for inputting the data and the code into computer's memory. So each of these architecture still remains up to this moment. Von Neumann architecture does not require two different types of memory, and that's why building computers using von Neumann architecture may be more financially efficient. So they can be more versatile, and this may be the reason why they are used for today consumer electronics. While hardware architecture has its own benefits, for instance, security is much better here because no inconsistencies in data can result in corruption of the program, of the code. One of the kind of plagues of today security systems is the possibility of an attacker to modify the code in computer memory by cleverly forging some pieces of data which will result in a buffer overrun, and it will replace the code of the program in computer memory with some carefully forged data pieces that actually look like code, and they will be executed by the control unit, and then everything can go the wrong way, I would say. So one of the typical attacks is of this sort. While in Harvard architecture, this is just impossible. So if you have clear separation between the memory which stores the code and the data, then, well, of course, something else can go wrong, but not at least this kind of stuff. Not that the code will be overwritten with some strange data. Also, Harvard architecture enables more efficient processing of data. If there is a large amount of data, we have two separate buses here. So one channel connects the CPU with the memory which stores the code, and the other channel connects CPU with the memory, with part of memory which stores the data. And that's why we can use, say, some specific architecture of this connection between the CPU and the data storage to enable faster retrieval of the data from the storage and use a different kind of connection to retrieve commands. Then this can be done just more efficiently than in von Neumann architecture. And so for some specific electronics, for microcontrollers, von Neumann architecture is used not as extensively as Harvard architecture. So let's now talk about first high-level languages which appeared at the time. Well, actually, the first languages were not high level. When we speak about high level and low level programming languages, so there is a way to distinguish between them based on how close the system of commands of the language is to the actual hardware language that is used in the machine. So originally, there were no languages at all to program the machines. There were punch cards, and a punch card definitely doesn't look like kind of a language. There are no words, there are no tokens there, no expressions. So something that we're really good used to in the programming languages that we use nowadays. Then after punch cards, well, and actually before punch cards, to program some devices, people just had to manually press some buttons or connect plug some cable into a particular hole. So it was really tedious. Now, after punch cards, people started using a way to describe the program using some letters at least. And this was the beginning of the assembly languages. So still the commands were exactly the commands directly processable by the target computer. And people had to learn each time a new computer appeared, people had to learn from scratch the system of commands directly supported by the CPU of that computer and use these commands to write programs. But then it turned out that, well, you cannot do this forever, so you have to have some generic way of describing algorithms, because the more machines you have, the more tedious it becomes to rewrite the software from scratch for each new type of machine, right? And so the first programming languages started to appear. One can argue that the very first programming language, which can be considered high level, was a language called Plan-Calcul, devised by Konrad Zuse. So remember, that's the guy from Germany who built one of the very first digital programmable computers. But this language, Plan-Calcul, was not actually a language directly usable on a computer. So you couldn't compile a program in this language into something runnable on the computer. This was rather just a way to formally describe a program. So there were some rules of how the program in this language should be written, but this was rather to just describe what's going on. So this was a language used between engineers to store the ideas behind a computer program. Still, this manually then should be translated into the system of commands of a particular computer. Now, the first really usable high-level programming language was the formula translating system, or Fortran. And this is the language that actually had its compiler. So you could write a program in Fortran and compile it automatically into a program in machine language, so that it can be directly run on a target computer architecture. So here at the bottom of the slide, you can see an example of a program that finds the largest value in an array of numbers. And well, as you can see, this program has quite a lot in common with modern programs. So there's assignments, so there is indexing of an array, there's an if condition, although as we can see, there is no then keyword, and the loop doesn't look that familiar. Probably, well, still we have the words do and continue. After the word do, we have the address, like kind of virtual address, not physical address. Label, we can say, the label of command, which constitutes the end of the loop. And so here we have already quite a lot of concepts that later were introduced in the subsequent programming languages. That's already definitely not kind of machine code and not a punch card. Okay, so after Fortran, in several years, many influential languages appeared. So one of them was Lisp. This is abbreviation from Lisp processor. And this language found its inspiration in lambda calculus. Recall that alternative way of describing general computation, alternative to Turing machine. So that's lambda calculus by Alonzo George. Lisp was, I would say, quite ahead of its time. So this language allowed for uniform description of the data in forms of lists. So anything can be described as a list. An array of numbers is basically a list of numbers. A number itself is a list of zeros and ones, if we treat it as a binary number. Or we can say a list of digits from 0 to 9. A program itself is a list of commands, right? So, and a command itself is a list of arguments and operations. So instead of saying that A is equal to B plus C, we can just write down a list. A, comma, plus, comma, B, comma, C. So this looks unfamiliar for those who do not have any experience in kind of prefix notation or Lisp in general or lambda calculus. But we'll actually see where the power lies there and why one can consider writing in Lisp even today. Although this is an old language, there are some modern dialects of Lisp that are extensively used for, say, web backends like Clojure. Okay, so we'll not dive into details of Lisp language right now, because we'll do it later on when we consider some examples of lambda calculus, and we'll dive into details of Lisp syntax. So one other language worth mentioning is COBOL. You see that these are just consecutive years, right? So Fortran, then Lisp, then COBOL. And COBOL was a language specifically designed for being used by kind of ordinary people. So not just by engineers who were accustomed to using even machine code, but also by just people who understood plain English. And so in COBOL, for instance, instead of writing that C is equal to A plus B, you could write that add A to B giving C. So you can write program using plain English. Well, to my opinion, this doesn't solve the problem quite well, because you still need to exactly memorize the structure of the sentence that you should use. So maybe that's kind of not deep, but rather a shallow simplification. But well, the program was considered to be more readable. COBOL was used extensively by Department of Defense of the United States, and the language owes this department partially its fame and its wide spread. So one of the things that language introduced was records. Here you see an example of a record describing a student in COBOL with description of types. For instance, the name of the student is an alphanumeric string of length at most 20. The date of entry is itself a nested record with year being a 4-digit number and month and day being 2-digit numbers. And ECTS points is a field of this record that is a floating point number with 3 digits after period. So here we see the example of a concept that was introduced as early as this first wave of high-level languages. Okay, so next comes probably the most influential language of them all, of this first wave, that's ALGOL 60. This was not the very first version of ALGOL to appear, and still this was probably the very first standardized version of ALGOL. So here we have an example of a procedure for transposition of a matrix in ALGOL. You can see that it looks much like Pascal if you ever programmed in Pascal language. We have the definitions of the variables here, so that we have an array named A, an integer number, and so these declarations is a common thing in a language, right? Before we use a variable, we need to declare it. Here we have a for loop, a nested for loop. We have a standard assignment operator, indexing of an array using square brackets. So the program looks quite familiar, although it's written in a language which is decades old, so more than half a century old. So ALGOL 60, by the year of its standardization, was praised highly by many computer scientists. And Tony Hoare, one of the classics in this field, even said that this language was so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all of its successors. So a very important trait of this ALGOL 60 language was that it was a maybe first fully standardized language, in the sense that the grammar of this language was completely mathematically determined. And to be able to standardize the language, a special form of writing down the grammar was used, which was then popularized and kind of used extensively by computer science community, which is called the Backus-Naur form by the two of its designers. So this form breaks down some syntactic structure of a language via other syntactic structures. So this is a way to kind of recursively define what can constitute a valid program in a language. Here, this is just an excerpt of the whole language grammar. The whole description of the grammar using Backus-Naur form is much larger, but still quite graspable. And here you can see the kind of recursive definition here. So you can see that some portions of program are deterministically expressed via some other portions, like if clause is a word if, then comes a Boolean expression, then comes the keyword then, and so that makes us an if clause. So if you look up a notion of Boolean expression, you will also find its formal description in Algol 60 BNF grammar, not just in this excerpt, of course. So we can see also that an expression is an arithmetic expression or a Boolean expression or a designational expression, whereas arithmetic expression also breaks down into some structures. So it can be an if-else, or it can be a simple arithmetic expression. And simple arithmetic expression breaks down into terms which are joined by addition operator, a kind of adding operator, which can be either plus or minus, right? And term is either a factor or a term and the factor joined by some multiplying operator, which can be either star or slash, so either multiplication or division, etc. So this way of recursively define a grammar of a language is a very common way nowadays. And we have plenty of examples of recursive definitions in computer science. So this was one of the very first application of a recursive definition of grammar in computer science, and this is the year 1960 when BNF, one of the standard modern computer science tools, was designed. So being fully standardized, Algol gained much traction because before that, like the previous versions of Algol, for instance, the very first that appeared in 1958, it was not as extensively standardized. And thus there existed some dialects, some misunderstandings of like what exactly is possible to write in a language and what is impossible. And when you have a standard for a language, this greatly simplifies the popularization of the language, and this kind of glues community. So this language also had some traits that not all of them were as popular as in the days of Algol, but some of them are still notable. One of them worth mentioning is that this language implemented call by name. This was actually criticized by many, but nowadays functional languages, they do implement, many of them do implement the call by name strategy. So what is a call by name versus call by value? This is a way in which you pass parameters to procedures, to functions in your computer program. So one way is a call by value. When you call a subprogram, a procedure, all its parameters are passed as their values. So just if you have a variable named a parameter named a, if at the time of the call of the procedure this value of a is 5, then actually number 5 will be passed instead of like some abstract name a. While in Algol, the name of parameter is going to be passed, so to say. Well, the implementation, of course, is just has to be detailed, but still. And the name will be used, not just concrete value of that name. And this allows for some tricks, like one of them, which is in this slide, is called Jensen's device. Some clever tricks that can be accomplished only if your language supports a call by name. So let's kind of dissect this example. So here we have a procedure named sum, which has 4 parameters, 4 arguments, k, l, u, and ak. So here the procedure involves a for loop where we go from 1 to u, from 1 to upper bound, this parameter k, and we accumulate something into variable s. So you can see like the standard accumulation type of procedure. But now we can use this procedure and the call by name way of Algol to compute the sum of elements of an array, for instance. So because in this procedure sum, we do not have any arrays really. So as you can see, inside the sum procedure, there are no arrays. But if elsewhere in the program we have an array, say, called v, we can call our procedure sum with passing it a particular set of names, like I, 1, 100, and vi. And the point is that vi, v sub I, or v brackets I, well, this is a standard way, of course, to denote the ith element in an array called v. This will not be a concrete element of an array v at the time when this procedure is called. This will be passed as a name inside the procedure sum. And so instead of ak, we'll have v sub I. And if you look at this line which accumulates the values into s, so s equals to s plus ak, there we'll have s equals to s plus vi. And thus we'll be able to sum up an array. Note also that the k name, the name k, inside the procedure it's named k, but we pass I, the symbol I, as the substitution for this name. And so the for loop will then look like this, not for k equal from 1 to u, but rather for I equal from 1 to 100. And so this will result in a for loop like for I equal from 1 to 100, s equals to s plus v sub I. So we'll actually be able to access individual elements of an array inside this procedure one by one and sum them up. And this is a pretty tricky thing. So if you look at this program from the standpoint of like a modern programming language like C or Python, this is kind of a strange way of accomplishing things, right? But it can be pretty handy because instead of passing an array, you can pass an expression here. So you can, instead of vi, pass something like I squared. And then this same procedure sum would be used to compute the sum of squares of first, say, couple of integers. It can be used to integrate, to compute integrals. If you pass it a formula that computes the value of some function, right? So this allows actually for higher abstraction than could be possible if we didn't have the call by name way of calling procedures. And this is one of the strengths of Algol, but on the other hand, it's hard to implement efficiently. And at the time, it was criticized for being kind of an obscure feature of the language. Of course, the number of languages exponentially increased after these first languages like COBOL and Algol and Fortran and Lisp were introduced. Because there were more and more problems to be solved and more specialization needed for the languages to be fit for a particular problem. And so nowadays we have like a vast zoo of languages. So naturally here on this diagram, it's just one fraction of all the languages out there in existence. And if we also include dialects of existing languages and versions of languages, there will be even more. Still, those languages that we've mentioned, they, up until now, they influenced lots of syntactic and implementation details in how modern languages are implemented. So if you want to really dive into details in implementation of languages, I would recommend you one single book called Programming Language Pragmatics by Michael Scott. So it's currently, I think, in its 4th edition. And this is not an easy read, but like considering the size of this book, it is not just possible to cover everything that's in this book in our course. But if you want to dive deeper, this is, to my opinion, the book to read on programming languages, on all aspects of implementation of programming languages today. So we'll cover not like the course material will be covered not by this book only. So sometimes I borrow diagrams or examples or material from other books. But if I were to recommend only one, this will be it. Okay, so that is all for our short excursion into the beginnings of programming, the beginnings of programmable machines and computer programming languages. And in the next session, we are going to consider in more detail the existing zoo of programming languages and to actually understand like why it might be beneficial to learn many programming languages instead of just sticking to one of them.